Okay, for the last part, we're looking at, so part 3 in chapter 10, we're looking at Kepler's laws of planetary motion, which is lots of fun. And we've been doing some history discussion here. So let's look at who was Kepler. Okay, so Johannes Kepler lived from 1571 to 1630. And so he was a German mathematician and astronomer. He was trying to find work in those days, which wasn't easy for someone who's a mathematician and an astronomer, going from city to city, trying to find a patron who would pay him. Um, and one thing he did was he wrote a book of moon tables, which were very important for navigation because if you knew what time the moon would rise on each day, then you could compare that to the time that you saw the moon at your location. So Kepler wrote it for England. And what if you were in Brazil or close to it? Well, if you're out on the ocean and there's no land to look at, then you can look at the moonrise and say, this is 5 hours different than it is in England. So therefore, I know where I am. At least you know your longitude, which is the hard part usually of knowing where you are on the planet. So latitude is easy, longitude is hard. So he sort of got a little famous for that. He was wandering around. His family was dying off from the plague and fun stuff like that. Um, Kepler was kind of a middle class guy. Occasionally had to run back to his home city in Germany so that he could rescue his aunt who was being accused of being a witch. Anyway, so his family was dying off. I think eventually he ended up with just one daughter left. Um, and then he got hired by someone. So anyway, so Kepler's famous for developing 3 laws of planetary motion. So let's go see the guy he got hired by. He got hired by Tycho Brahe, or Tycho Brahe, as he's also called. He lived from 1546 to 1601. He was more higher class, aristocratic. He was the Danish royal astronomer and alchemist. So he was hired by the Danish court to look at the stars and predict things, or at least know when the eclipse is coming. But Tycho, he realized that to do good astronomical work, you really have to work at it. You have to be out there every night, systematic, rigorous observation, night after night. So he wasn't just playing around, he was out there taking measurements. And boy, did he take good measurements. He built wonderful place called Stellenbergen, which means Star City, and it was on an island, I believe. And he would take measurements there. He had the best quadrant in the world. Now, this was before people had telescopes. So what he did was the quadrant. What it did is basically you would aim a tube at a star or a planet and you would read that angle off. Okay, so that's what you got. You didn't have a telescope to bring it to make it look bigger. So all you could tell was where that star was located or that planet. And so every night he'd be out there and he and his assistants would be getting the locations of all the planets every night. But then he had a lot of data. He wanted to know what the orbits were, but he really needed some help. So he decided to hire Kepler to help him figure out the orbits of the planets. So he hired Kepler and he brought him to the observatory. And Kepler said, "Oh, can I do Jupiter? It's like the best." And Tycho said, "No, you can do Mars." So anyway, forgive the Danish accent there. He said, "No, Kepler has to do Mars." As it turns out, it was fortunate that Kepler did Mars first because Jupiter has an orbit that is almost perfectly circular. So probably Kepler would have just thought all the orbits were circular. But Mars has the most elliptical orbit. And so that is what he figured out. Now, Tycho's data was fantastic. His data was precise to within 1/60th of a degree. So this was amazing. Anyway, so Kepler came and Tycho hired him. Now, Tycho wasn't very good about letting the data go. Kepler had to sneak down, the story goes, in the middle of the night and break into the box where the data was kept, because Kepler wouldn't give him all his data. I mean, this was his, I'm sorry, Tycho wouldn't give him all the data. This was his life's work. He wasn't just going to hand it over to someone. Anyway, now a little bit more about Tycho. You may notice here that his nose looks a bit odd. Well, that's because sometimes this painting, that nose is golden colored, because Tycho actually had a fake nose. When he was in college, he did well on a math test, and another student challenged him to a duel over the math test. And so they fought, and his nose got cut off. So poor Tycho was forced to have a fake nose the rest of his life. And it's amazing that he survived. Anyway, so I'm glad students don't fight duels over math tests anymore. And also, though, Tycho, even though this was after the time of Copernicus, remember Copernicus and the heliocentric system that put the sun at the center? Tycho wasn't sure that the sun was the center of the solar system. It made sense what Copernicus said, but the problem was Tycho was having trouble seeing that the Earth moved, because he could not see the parallax motion in the stars. So when the planet Earth moves, so let's say you're on Earth and it's, June, and then later it's going to be December. Excuse me. And if you were looking at a star up here, well, from June, the angle of the star would be like that. In December, the angle of the star would be like that. And you should be able to see a different angle if this planet Earth was actually moving. But Tycho couldn't see a different angle. Now, he didn't even have a telescope yet, so that's why. And even after you have a telescope, the motion of parallax is so small, because as it turns out, the stars are so far away. But nobody knew how far away the stars were. So Tycho thought, well, maybe the Earth isn't moving. So he felt all the planets were going around the sun, but he made the sun go around the Earth. So this is the Tychonic model of the solar system. The Earth is in the center, the moon goes around the Earth, the sun goes around the Earth, but all the other planets go around the sun, which is pretty cool. So it's kind of halfway between heliocentric and geocentric. Okay, so anyway, so poor Tycho, what happened was that he died. After he died, the story goes that Kepler went down and stole all the data from the locked box and figured out all the orbits of the planets. Now, that data didn't really belong to him. And in fact, there was a lawsuit that the wife and children of Tycho sued Kepler for stealing the data. And of course, there were rumors that Tycho had been poisoned maybe by Kepler. Well, you'll be happy to know that Kepler did not poison Tycho Brahe. Recently, poor Tycho was dug up, and they found out that he died probably from cancer. Anyway, so yes, so he did not die from poisoning. All right, so anyway, so back to the 3 laws of planetary motion. The first law is called the law of elliptical paths, which just says that, yeah, all planets move in elliptical orbits around the sun, and the sun is one focus or foci of the ellipse. So back on this picture here, where the pins are would be the foci. And you can move those closer. You can even put them on top of each other. That would be like a circle. But they would show how the degree of the ellipse is. So the further apart they are, the more elliptical the path is. So anyway, so this shows a really elliptical planetary path, which none of the inner planets actually travel a path that elliptical. But the sun would be at one focus, and then there would be another focus over here where basically nothing is. Okay. So the 2 foci are where the 2 pins are. Now, for the Earth, the orbit is a little bit elliptical. The average distance between the Earth and the Sun is called an astronomical unit. We'll need to know that. So it's called an AU. And that is 1.5 times 10 to the 8th kilometers. But you can also, of course, remember I talked about the distance between the Earth and the Sun as 93 million miles. Okay, so that is one astronomical unit distance between the Earth and the Sun. Okay, we'll need that for the third law. Okay, now the law of equal areas was his second law. Kepler really was a brilliant guy. I mean, he didn't have the distances to the planets. He just had angles, right? Nobody knew how far away the planets were. He had to figure that out. And he had angles from a moving reference frame. The Earth was moving. You know, if the Earth stayed still, then it would be much easier to figure out the orbits. But the moving Earth, that made it difficult. So anyway, so the second law is called the law of equal areas, which is another brilliant thing he noticed. When he laid out the planets in their orbits, he noticed that during the same times, so let's say this is 30 days, so like 1 month, and over here it's 30 days. But you can see how the planet moved a lot further in January than it did in July. And yes, by the way, the Earth is further away from the sun in July when we receive the most sun in the northern hemisphere. That's because of the tilt, not because of how close we are to the sun. So anyway, so the perihelion is where we're closest to the sun. The aphelion is where we are furthest from the sun. And so when you plot that out and figure out the area, these areas are equal, which is very strange. Now, it does have some meaning, though, beyond that. It has to do with conservation of energy. Because that means that 30 days here cover greater distance, so it's going fast at the perihelion. And at the aphelion, it's going more slowly. It doesn't go as great a distance. And so in July, which is coming up soon, the Earth will be moving its slowest at that point. Okay, so what does this have to do with energy? Well, remember conservation of energy. Planets have conservation of energy too. So they can have their potential energy, their distance from the sun, and their kinetic energy. And so what happens is that has to remain a constant, right? The mechanical energy is a combination of those two, and that is going to equal a constant. Okay, so if the potential energy varies, the distance to the planet, then that means the kinetic energy has to vary also. So what's happening in an elliptical orbit is when the planet is furthest away and it has large amounts of potential energy, then its kinetic energy is small. So big potential energy, small kinetic energy, and it moves slowly. When the planet is closer to the sun, then it has small amounts of potential energy, so the kinetic energy goes up to compensate, and now the planet or satellite is moving fast. Okay, so conservation of energy is part of this. Okay, now Kepler's third law is called the harmonic law. And this is an equation that you will have one on the test. The equation is t squared equals k r cubed, where t is the period or time of one revolution. So we usually do that in years. So that would be time for an orbit, like for a planet around a star. R is the length of the semi-major axis, so that's the distance. Okay, so that would be like the orbital radius. And then that's why it's r, so radius. And k is just a constant. That is basically 1. And it just adjusts for the units, years squared over astronomical units cubed. Because your radius, we're going to do in astronomical units. Okay, remember that's the distance between the Earth and the sun. So for the planet Earth, it's easy. The period is 1 year. The radius is 1 astronomical unit. So we've just got ones all through there. That works. For other planets, though, we can have more fun. So let's look at this for some other planets. So for other planets, let's use that law. So t squared equals kr cubed. Okay, so let's try this. Now, Saturn is at about 10 astronomical units from the sun. So for Saturn, r is equal to 10 AU. Let's find out what the period is for Saturn. Okay, so what's the period going to be? The time that it takes to go around the sun. Well, K is just 1. But what it does is it fixes up the units. It's years squared over astronomical units cubed. Then we're going to have our 10 astronomical units, our radius cubed. Oops. Put the AU in there. Okay, so let's cube that. And that's going to be 1 year squared over astronomical unit cubed. And of course, we're going to get 1,000 astronomical units cubed here. All right, so you can see what's going to happen maybe here. The astronomical units cubed here is going to cancel here. So what we end up with then is t squared equals 1,000 years squared. So now I can take the square root of both sides and end up with t is equal to the square root of 1,000 years squared, which of course the square root of 1,000 is 31.6. Let's just round it to 32. And the square root of years squared is just years. So there I end up with the time for Saturn to go around the sun is 32 years. Isn't this great? You actually now have this cool power to figure out the period for a planet. So what you should do is try this for a couple of planets. Let me write down some values for those. Okay, so if you want to go way back to something like Mercury, it has a radius of around 0.3 astronomical units. For Venus, it's around 0.6. For Earth, of course, it's 1 astronomical unit. For Mars, I always have trouble remembering Mars, but it's around 2. Okay, for Jupiter, it's around 5.5. Saturn is about 10. Uranus is close to 20. And Neptune is close to 30, while right now Pluto is close to 40. But Pluto has such an elliptical orbit, sometimes it's only at 30. So it varies. It comes within the orbit of Neptune. So Pluto has a very elliptical orbit compared to the other planets. Okay, so, but right now it's about 40 astronomical units out. Anyway, so what you can do is pick one of these and figure out how long the period is, or pick some of these and practice using that formula and figure out how long the period is. Really, it's very simple. Basically, it's cube it, then take the square root. So that's basically the steps that we did. We cubed the 10 to get 1,000, then we took the square root. And that's basically the step. So if we just did Uranus, we would cube 20, and that would give us 8,000. Then we would take the square root, and we would get 89 years. Okay, so anyway, so it's really easy to do. Just cube it, then square it. And that's the only way I'm going to ask you to do it. I mean, I could make you go the other direction, give you the period, and make you square it, then cube it, but take a cubed root, but I don't do that. Okay, so anyway, so yeah, so it's pretty cool. You can easily figure out the number of years it takes, Earth-type years, for a planet to orbit the sun. All right. Okay, so another thing in there is escape speed. What's escape speed? Escape speed is the speed that an object has to go to never have to come back. So it escapes the gravitational influence. Is that right? No, well, there's still some gravitational influence. But what it does, it is escapes it. So it's still being pulled by gravity, but it's so weak by the time it gets far away that it can keep going. Okay, it's always the speed that it can still keep going. Gravity never pulls it back down. Okay, so it never goes into orbit. For the planet Earth, that turns out to be 11.2 kilometers per second. And for all the other planets, well, it depends on the mass and the radius of the planet. And so something like Jupiter, you have to be going 60 kilometers per second. For Mercury, you only have to be going 4.3 kilometers per second. So anyway, so yeah, so some things are definitely easier to escape from. And other things, like here's the sun. The sun, you have to be going at a distance of Earth's orbit, only 42. So actually, Jupiter right from the surface would be 60, although Jupiter's surface is a bunch of clouds. Okay, so anyway, so that's what that chapter is about. Now, do we have anything that we have sent away that is going the escape speed? Yep. Pioneer 10, Pioneer 11, Voyager 1 and 2 have all basically escaped the influence of the sun. They are headed out of the solar system. So they have reached the edge of the solar system at about 100 astronomical units already. And so they are going out into space and never coming back. Okay, that's the end of that talk.